We have the pleasure of hosting Valery Vishnevskiy today for the talk. Valery did his master's degree from Moscow State University in 2011. And then he did a PhD degree from ETH Zurich, and he graduated in 2016. And since then, he has been associated with the Institute of Biomedical Engineering at ETH, and he's working as a senior scientific assistant with Professor Orcun Goksel and Professor Sebastian Kozerke. And his research interests are around image reconstruction problems, but also around inverse imaging problems in general. So today, Valery will talk about model-aware neural networks for image reconstruction, for, I believe, flow MRI as well as CT reconstruction. So yeah, we are looking forward very much to the talk. Valery.
Yes. Thank you very much for introduction and for invitation to present on your seminar. So as was announced today, I will talk about image reconstruction. So even though I had my original training was in applied mathematics, medical imaging is actually a field of physics because it all starts with the physical experiments. You take a subject or sample and put into a medical scanner. In this case, it's MRI scanner, and you conduct a physical experiment. In case of MRI, you apply some radio frequency pulses to excite the tissue and to measure the signal. And the measurement signal, in case of MRI, it's called the K-space, is the data that we gather from the scanner. And the people who designed this experiment, the physicists, their job, or their main aim is to provide the forward image synthesis model. So to model the physical acquisition process. And in overwhelmingly many cases in medical imaging, the base model, the base forward model is a linear model. And then knowing this functional dependence between image and the acquired signal, given some noise information that we know about the acquisition, our aim is to reconstruct the image from the measured signal. So to revert the process of the encoding of the signal. So just to give you an idea where these methods fall in, if we look at the application of medical imaging in general in practice. So if you want to image inside a tissue or a subject, you first have to design the experiment and the acquisition pulse sequence, the type of ultrasound probe, etc. So the first part is designing the imaging experiment. The second part is the reconstruction, and it falls more into the field of the signal processing. So, and the main questions that we want to answer and the main knowledge that we want to leverage is the physical acquisition model, a good prior for spatio-temporal coherence of the signal, and an efficient method for inversion, for solving the system of equations. And then we produce an image. So at this stage, we don't want to put too much artificial intelligence in here because at the reconstruction stage, we want to know more like a low-level knowledge about image, the fact that neighboring pixels are very similar, etc. And actually, the artificial intelligence part comes after image reconstruction. It's called image analysis, for example, segmenting the image of the heart. And at this step, we would one of our aims would be to substitute the human. So that's the place where we want to be actually intelligent. And after we have imaging data and extracted the useful information that we had in mind, we can use it in some statistical population studies to see what kind of information can aid the diagnosis. And so as I said, the forward models for many imaging modalities can be described with a linear operator or in many cases with a matrix. And here you can just, to convince you, there is a list of different medical imaging modalities and that shows what is the structure of the linear operator that explains the acquisition process with this modality. So let's just quickly consider a standard example of computer tomography to see how the linear system is defined, right? So in the X-ray, we have X-ray emitter and detector array, and the X-rays penetrate the tissue, right? And then the more dense the tissue and the more the tissue is on the path of the ray, the more attenuation can be observed. And if we consider only one ray that is emitted from here and is detected at this point, we can say that the integral of this ray is equal to, the measured signal is equal to the integral of the attenuation coefficients. And those coefficients form the image that we would look at. And the integral, if we discretize it, it's just linear sum. So therefore, this relation that describes the measured signal is a linear one. And then if we write down these equations for all of our detectors and emitters, we arrive at the system of linear equations, which we can write down in the matrix form. And then obviously our aim would be to solve this system of linear equations in some sense. So that's just a small refresher how the linear algebra comes in imaging. And it's a similar story in case of magnetic resonance imaging, that instead of line integrals, what we actually measure is the inner products of the image with the corresponding spatial harmonics. So here you can see the signal that is acquired in the K-space, and each point in this K-space corresponds to the weighting of our image with the corresponding wave with the direction and period. So, all right, a lot of imaging modalities can be described with the linear systems. The acquisition process can be described with the linear systems. Now let's build up a mathematical framework that we need to consider it. So the synthesis model is the following, right? So the linear acquisition operator and the readout noise on top that can come from many sources in different modalities. So, of course, this system of equations can be inconsistent, so it can have it can have zero, it can have no solutions, and therefore a reasonable thing to do if the system is inconsistent is to try to find X that gives the smallest reprojection error with a signal that we measured, given the imaging model. And this is a least square problem. And of course, we can solve it analytically by just taking the derivative of this L2 norm and setting it to 0. And therefore, we have yet another system of linear equations, the normal equations, and it can be solved with a pseudo inverse. So this is model-based or iterative reconstruction methods are based on this approach. Also, you can, instead of solving the system of this least square problem analytically, you can also apply different optimization methods on top of it. For example, you can do a gradient descent on this cost function, and then actually the one of the first reconstruction algorithms, the back projection, can be seen as a single step of the gradient descent that is initialized with 0. And actually, so if this imaging matrix is orthogonal or unitary in complex case, then this will be also the solution, the exact solution to the optimization problem. Okay, but in many cases, especially for computed tomography types of problem, if we just apply this formula in a straightforward manner, so, and actually this example is the deconvolution problem. So you can see that our measured signal is a smooth image. So this linear system is poorly conditioned. So if we will calculate this formula as given here, we'll get an unreasonable solution, and you can see that the pixel values go to basically infinity, 10 to the power of 6. So in many scenarios, this doesn't work. So what we need to do is the regularization. And to see why we need regularization, you can consider the eigen decomposition of the normal matrix. So we take eigen decomposition to characterize this solution given by the pseudo inverse, right? And if we know the eigen decomposition of the normal matrix, it will be the product of U, which is orthogonal matrix, diagonal matrix with eigenvalues on the diagonal, and U transpose. So of course, this we introduced this decomposition to calculate the inverse matrix, and we see that if we when we invert the matrices, what we do is we actually invert the eigenvalues, and if one of the eigenvalues gets too small, then you basically multiply the noise by the very large number because you take 1 over eigenvalue alpha. And therefore, the measure to characterize the ill conditioning of the matrix is the ratio between the largest eigenvalue and the smallest eigenvalue. So to do that, we introduce the regularization. So from Bayesian perspective, we can build it up from the Bayesian perspective. We can introduce the regularization, but also it's very intuitive because remember our solution just went to infinity. So maybe instead of only optimizing the reprojection error, we also want to penalize the solution to get there too high in its magnitude. So we add this penalty regularization term. And then it's still a quadratic optimization problem. We can take the derivative and write down the closed form solution. And you see that now instead of inverting matrix ATA, we add a small diagonal identity matrix to it to kind of smooth out the inversion of the eigenvalues of the matrix. Now, in real imaging applications, we rarely penalize just the magnitude of the image. We want to actually employ the spatial coherence of the images. And to see that, consider the distribution of the differences of the neighboring pixel intensities. And if you just take 2 images, the images with high signal to noise ratio and low signal to noise ratio, you can see that those distributions are different and they depend on SNR. So our main aim is to employ the regularization on the neighboring pixels. And we do that with the spatial finite differences. So if you plot now the histogram of the final differences, you can assume some distribution over them. And 2 popular choices is the Gaussian distribution or Laplace distribution. And then you can fit them. They have 2 degrees of freedom, right? The mean and the variance. And assuming parameterizing them as such, you can tune them and see which one fits better. So in this case, we can see that Laplace distribution is a better approximation. It's a better explanation of the image gradients compared to the Gaussian distribution. And if we employ this prior over the distribution of image edges, what we will actually do, we will minimize the L2 norm of the magnitudes of the spatial image derivatives in case of Gaussian prior, and the L1 norm in case of Laplace prior. Right, so this is this formulation is very generic and very standard formulation of the image reconstruction problems. And if you look at it, now we have to solve this problem. And what are the ingredients that we need to solve it? Well, first we we have to know the forward model from our imaging experiment, and it's fixed. Then we have to know the noise statistics of our acquired signal. And the L2 norm means that we assume the Gaussian acquisition noise, and L1 norm would again assume the Laplacian acquisition noise. And then we would need to find an optimization method to solve this problem. And also on top of that, we have to tune the weight of the regularization. So how much of the prior knowledge do we want to incorporate in our resulting reconstruction? And usually the first three points are fixed. So we know something about acquisition, and usually in modal-based reconstruction, if we can solve the optimization problem properly, we don't really care what method achieves the solution, because if the problem is convex, the solution is unique. However, the regularization should be tuned, and we usually have a sweet spot for the regularization value, somewhere around here, where we balance between our prior knowledge and the acquired data influences. In practice, if you implement one of the reconstruction algorithms, you tune this regularization parameter by, for example, if you have a couple of we can call them already training images or like simulated images where you know ground truth, you can just grid search the value of the regularization parameter and pick the best one, right? So it's already posed as a learning problem. However, in this case, we had only we have only one parameter to tune. You can imagine that we can add a few penalties, few sort of regularizations. And then if we add a few different terms, then we will have to tune multiple different regularization parameters, and we cannot grid search in high dimensions. So what we would like to do is to employ the methods from convex optimization by taking the gradient of the expected reconstruction error with respect to the regularization parameter that we are trying to optimize. Now, can we do that? So, well, if we apply the chain rule to this expression, well, we obviously can differentiate through L2 norm, right? But then we have to take the derivative of the reconstruction with respect to the parameter, to the regularization parameter. And well, symbolically speaking, we cannot just move the gradient operator into argmin. And that's the main issue. So in case of Tikhonov regularization, that is assuming that we have Gaussian distribution of the image gradients, we have a closed form solution again. And if you consider it, this expression involves some matrix multiplications and inversions, and those operations are differentiable. So for standard L2 regularization, we can compute the gradients with respect to regularization parameter in a straightforward manner. So it's all implemented in autograd tools like PyTorch or TensorFlow. However, for total variation regularization, where we take the L1 norm of the gradients, there is no closed form solution. We have to use iterative methods to find one. However, if you use any iterative method, you have a limited amount of time. You have to stop the iterations at some point. And usually for many problems in imaging, it can be something like 50 iterations of the method or 100. And we also don't want to iterate too much because early stopping of the optimization can be seen as additional regularization. So therefore, the proposition is to approximate this solution as the output of the kth iteration of the gradient descent. So we can write down these iterations. So this is just gradient of the cost function, right? And so, of course, in practice for this sort of problems, a gradient descent is not used, and it will be called subgradient descent. But in practice, it still can work, and it still will converge, but very slowly. But we start with this point. So let's now analyze this expression. So here again, we have some multiplications with scalars and some linear algebra and one non-linearity, right? So it's the derivative of the L1 norm, the sine function. And the problem here that if we will consider the iterations of this gradient descent as the neural network layers, we'll have to backpropagate through this non-linearity. And the sine function being a step function, its gradients are zero almost everywhere, right? So we will not have any meaningful gradients from this formulation. But what we can do is we can start to relax the this method. So instead of using the sine function, which is the derivative of L1 norm, we can use the smooth step function. You can use sigmoid for that, or some other approximations. So after we substitute it and make everything differentiable, now we consider each iteration of the gradient descent as one layer in the neural network. And all operations here are differentiable. So we can backpropagate and calculate the gradient of the output with respect to parameters that we are interested in. In this case, we're interested in the regularization parameter. So we want to tune the best fitting prior and also the step length, alpha. So how to optimize it as efficient as possible. And let's say that those are only the trainable parameters at this point. So at each iteration, we learn the step length and one global regularization parameter. And our model, it is inspired at this point by the gradient descent of some model-based formulation of the inverse problem. But it's differentiable, and we can minimize the expected reconstruction loss in a standard way over the training sample. And in this case, the solution will not be the maximal a posteriori estimate that is based on our probabilistic model that we initially constructed. It will be the mean of the posterior that is assumed. But okay, so at this point, it's not really a neural network, right? We have only around 11 parameters to learn. So, what we learned is at this point is how to optimize our cost function and how to choose the regularization weight. But we might want to introduce more degrees of freedom here. So why did we fix the convolution kernel? So why did we choose to penalize the spatial differences of the finite difference of the image? We might want to tune that. And so we relax those iterations in the following way. So first, our convolutions, they can be different at each unrolled iteration. The second thing is that we don't tune only one convolution, we tune the bank of convolutions or filters, NF filters. And also we unrolled this gradient of the regularization term, assuming that we penalized L1 norm of the regularization. Why L1 norm? Maybe there is something more optimal. So let's call this activation function phi and learn it as well. And this is the standard iteration of the vanilla variational networks that were originally proposed by Keskin, Hamenik, and Thomas Fock. So at this point, yet to reiterate, we learn the step length, the convolutional filters, and the activation function at each step. So small just a short detail about the activation functions. So in regular neural networks, what we usually have is ReLU, right? And ReLU doesn't have any learnable parameters, but there are some other modifications of ReLU, like leaky ReLU, where we can change the slope of the piecewise linear parts of the function. So we can extend this and actually parameterize our activation function just with a linear interpolation on a grid. So we assume that this phi of t, that the argument t can range from -5 to 5, for example. And we place a grid of control nodes in this range. And then we just tune where this control node should go, up or down, up or down. So, and that's how we parameterize the activation functions. Another technical detail is that we, to improve the generalization ability, we want to constrain the filters to be zero mean and unit norm. And there are a couple of ways how can we do this, but we chose to do this by just a simple reparameterization. So we have the variables d that we optimize with respect for, and then we reparameterize them to be zero mean and unit norm, right? All right, so that's the standard, that's introduction to variational networks. As it was introduced by Haminik for magnetic resonance imaging, it was the following architecture was used. The gradient, they enrolled the gradient descent algorithm, 48 convolutional filters of size 11 by 11. And for each of those filters at each layer, there was a tunable activation function that is parameterized by this 31 control nodes. And then you can see, look at the learned filters and the activation functions. So first, you can see that there are some directional information in these gradients, and they look reasonably coherent. And we also can analyze the activation function. Now remember that the activation function is assumed in some way to be the derivative of the cost function of the penalty. So therefore, if we integrate this activation function, we will get the cost function. And you see that some of them really resemble the L2 norm. Some of them resemble L1 norm. Some of them resemble truncated L1 norm, right? Where we don't want to penalize for very big deviations. And some of them are actually inverted, which means that those are not regularization or smoothing filters, but they are rather sharpening filters. And also a slide to convince you. So there are a lot of architectures for image reconstructions, and there are like a lot of families of architectures. And if we compare it to others that you can see in this list, the variational networks have the smallest amount of tunable parameters, and therefore the training size that is needed to learn this model is not too big. So that's one of the big advantages. Okay, so now the main confusing part is over, and I will talk through the further extensions of the variational networks and their applications. So just remember that our approach is to provide a prototypical optimization problem for image reconstruction, then choose the method to unroll and use some intuition from the numerical methods to add degrees of freedom that make sense to the model. So there are two problems that I will consider today, and we'll not go into details about the imaging process, but rather the data. We will look at this from a data perspective. So we had 4D flow MRI, and in this, we have a huge data set here. We have NT cardiac phases, so we image a beating heart, and NT is around 25. And then each 3D volume is something like 100 by 100 by 50. And this 4D array is acquired for each of the flow projections. so that we can then recover the 3D velocity of the blood flow in aorta. And so this is a huge image sequence, and we only have 11 of those images to train. And the idea here that to acquire this much data, you either have to put a subject into a scanner for like hour or two and wait for 2 hours, or if you use compressed sensing, so if you will acquire only part of the case space, you can accelerate the acquisition to like 15 minutes and then use the classical methods for image reconstruction based on compressed sensing. And the problem there will be that our reconstruction now very fast, acquisition now is very fast, but the reconstruction with those methods, even on the multi-core CPUs with GPUs, will take around 30 minutes. So we also want a speed in for a clinical practice. And so what problem do we have from intuition? If we have only 11 training samples and a huge vector to predict, well, we probably can get overfitting in there. And what can we do with that in terms of variational networks? Well, as I said, we have to gather some intuition from the classical methods. So if you will implement the optimization method for image reconstruction, you will see that the cost function goes smoothly to the minima. And all the intermediate reconstructions during this iterative procedure, for model-based methods, they look quite reasonable. However, for variational networks, it's not the case. So it doesn't follow this pattern. You can see that those are unrolled iterations. So the reconstructions at the unrolled iteration. And for example, at the very last layer before the output, the current estimate of the image looks quite unreasonable. And we don't even know if, like, is there any information contained this far in the flow of the network? So for us, for humans, it's really hard to say. But maybe let's force the network to behave like the classical methods. Instead of minimizing the loss for the last reconstruction estimate, let's minimize the loss on each of the iterations, and we will just add a weight on the iterations. So basically, we want to penalize the loss on the last layer the most, and on the first layers the least. And this can act as a regularizer because it constrains the possible configurations of the network. But also it can be seen as the thing that helps you to train the network, because you can gradually set tau to infinity so that in the end you will penalize only the reconstruction at the last layer. So this is for the generalization ability. Now, in the undersampled MR reconstruction, we have only part of the case space as an input. And usually the network is trained assuming the fixed acceleration rate. We know that we take only 1/4 of the all possible data. So we accelerate the acquisition by a factor of 4. And assuming that, people usually train the network. In our acquisition scenario, because the heart rate is not exactly periodic, and it can so the undersampling mask, the acceleration rate can vary from scan to scan. And then of course, we would assume that if we have all the acquired data, then we need less regularization than in case if we have very few of the acquired samples. So how to make one network to operate accurately enough on the range of the undersampling rates? Well, the idea here would be to modify our iterations of the gradient descent algorithm and to add additional modulator to the data term and the regularization term. And these modulators will be basically the same functions as we use for activation functions, so psi-d and psi-r. And they are the scalar functions of the acceleration rate. So or the mean acquisition ratio, sorry. So if we tune now those modulators, we can look at them. And this is also one of the advantages of the variational networks. We introduced some degree of freedom and we can actually analyze it. It's not just some neural network black box, it's just 1D function. It's very simple to plot. And now what you can see is that we can plot these modulators for the data term and the regularization term. And then you can see as we acquire more and more data, we put less and less regularization, right? If you look at the red line. And the data term is relatively unchanged with respect to the sampling rate. All right, so I will show you some results a little bit later. I wanted to introduce a few more tricks that are shared in this paper and also introduce a new modality. So it's ultrasound transmission tomography. So I will go very quickly through it. So the idea is that in the regular ultrasound images, what you see is echogenicity of the tissue. So the fact that here we see something bright means that there is some interface between tissues, or that just the tissue there reflects the sound a lot. And this is not very useful for diagnosing the, for differentiating the tumors. So what we want to do, we want to measure speed of sound. How can we measure it? Well, we either need to have the circular array. So here's for the breast cancer imaging. And as you can see, those machines are very large and expensive, which is not the point of ultrasound. The idea here is to use the reflector with the ultrasound probe, and then we emit and receive rays and can measure the delay between those. And because we approximately know the path of the ray, it is basically just a different formulation of a tomography problem, very similar to X-ray CT. So yeah, there is some pre-processing that has to be done to extract those time delays. And it is, but what is important in the end, we again arrive at the linear system. But the difference here compared to MRI is that in case of MRI for Cartesian acquisitions, our matrix, even though we had undersampling, the acquisition matrix was unitary. And the gradient descent works quite well for such well-conditioned unitary matrices. But this CT matrix, the ray matrix, because we have an access to the tissue only from the one side, right? We have only the readings from in this direction, so in the longitudinal direction, and we have no rays penetrating the tissue in the transversal direction. So, and in practice, it would mean that the acquisition matrix is extremely ill-conditioned. And now there are a few slides, but I think the easiest way to follow it is, what would you do if you were implementing the classical reconstruction method based on the models? Well, if you knew that you have a poorly conditioned acquisition matrix, called L in this case, by the way, well, first thing, you know that if we plot this level set of the cost function, if there are some elongated values like here, the descent methods will oscillate a lot and will even diverge. So what can we do to mitigate this? Well, first, instead of unrolling the gradient descent, we can unroll the gradient descent with momentum, right? We just program it in TensorFlow or PyTorch, and the formulas are not too much more complicated. And all these momentum terms, they can also be tunable parameters. And doesn't really matter how the formulas look here. They don't reveal a lot of things. It just works, and it's very reasonable. Oh, by the way, in terms of, in this specific case, the unrolling the gradient descent with momentum can be interpreted as adding additional skip connections. So there is one interpretation, but I don't really know what to do with that. What else can you do with poorly conditioned matrices? Well, you can use a preconditioner, right? If you have to solve this system of linear equations with a poor condition number, let's just multiply it by a non-singular matrix from the left called W here. And if W is approximately the inverse of L, then the resulting problem, this one, will be much better conditioned. And we will learn the preconditioner in the unrolled optimization. We can choose, so in this case, the preconditioner was just diagonal matrix. We can choose it to be a circulant matrix, so basically just to implement the convolution. Then the activation function, we assume that we have Gaussian acquisition noise. But if we're not sure about that, or if we have data from some simulator, we can also put an activation function to the data term, right here, just to add a bit more degrees of freedom. In case of this particular problem of ultrasound transmission tomography, as we mentioned, we have very anisotropic data. So you see that the longitudinal resolution is really low. We have a lot of blurring. But the lateral resolution, you can see some sharp edges. So that would mean that, and also you can see that different parts of the image are intersected by a different amount of rays. So we have a different amount of data for different parts of the image. So the idea here would be also to add to each filter its weighting profile, the spatial weighting profile. So that would mean that some filters are active only on the edges of the image, as you can see here, because we barely have any rays around here. And some of the filters are active only in the center. And so this W is the diagonal of this matrix, and this is just a spatial weighting. And yeah, I think, yeah, so I will try to wrap it up a bit faster. So you can write down this architecture just by documenting it or manifesting it. But what is the really important part is what kind of architecture to introduce to your specific problem. And then you train it as any other regression task. So one particular interesting thing about this ultrasound transmission tomography paper that we had is that we have no ground truth data because it's a novel modality. We don't know how to optimally sample the signal at this point. So we don't have any real training. If we even have a lot of time, we couldn't get this. So what we did is we just simulated a lot of, you see this sort of blobs to simulate the inclusions. And we modeled, so we simulated these delay vectors on a different resolution grid, so to avoid the inverse crime. But yes, so and actually one of the main results that we got in the end is that, of course, we could report how well we can reconstruct the synthetic data or data assuming our linear model. But in fact, the ray propagation procedure can be much more complicated. And the fact that we have good reconstructions in our simulations can mean nothing in practice. So what we did is we imaged phantom, so the breast phantom with two inclusions. So you can actually see them around here quite clearly, but what we are interested in is if we can detect the speed of sound change, because they have a different density. And so these two methods are classical model-based reconstruction methods. And this one is so far, I think, the best tailored and manually tuned reconstruction method for this particular problem. And what you can see is that those classical methods, they completely miss the second inclusion. And the variational network, even though we were very afraid that it would overfit on the synthetic data, or what is more important, that it would overfit on the synthetic imaging model. But in practice, we could detect both inclusions. Now we can also show that all these modifications to the variational network that we did, they improve the reconstruction accuracy. And well, if it didn't, we wouldn't incorporate them. But I don't know what conclusions one can make out of it, because that's just the experimental, like it's purely phenomenological. And it just supports the fact that the reasoning was valid. And the same is true for the MRI example. All right, so now to sum up, what is the main message? The main message is that from our perspective, for the many reconstruction problems, the unrolled methods are provide a favorable trade-off between the size of the model, the amount of training data needed, and the quality of the reconstruction. And also it has a very strong basis that, well, we could do reconstruction without any machine learning for years now, and it was actually quite decent. The problem was that it was quite hard to choose the specific regularization, the specific numerical method, and also implementing the numerical method can be very, very complicated. And the neural networks just help to mitigate those small edges and maintaining the main idea behind it. And to make you a bit more convinced, just want to point out that in case of ultrasound transmission tomography problem, what we were surprised at is that we could reconstruct the real data using only the simulated using only synthetic linear model without assuming any wave physics. And also we applied the variational networks for very ill conditioning operator. And in case of 4D flow MRI, we could train with a very limited amount of data and for not predefined sampling pattern. And if you think about it, it can be quite it can come quite strange from the first glance, because usually when there are a lot of problems that can be approached with machine learning, right? So one of the maxima, or like one of the rule that you can have like a soft rule, is that, well, I can approach this problem only if the people can solve this problem. Even if people cannot solve this problem, then maybe we shouldn't try to train machine learning algorithm for that. But in case of image reconstruction, nobody can provide without any computer. People probably will be very bad at reconstructing the image from the acquired signal. And so I think that this is so quite a rare example in this case. And also this model can be trained using very, very limited amount of data. And the outlook is that from my perspective, most of the reconstruction methods are already at the limit of amount of the data that we can extract from the signal. So a lot of papers report the improvements of 15 or 20% in the reconstruction accuracy, but unfortunately, most of those improvements are shown in the synthetic experiments. They can change the data, so they have they divide the test and training data sets. But what is more important here is the synthesis model, so how we simulate the synthetic measurements. And this is what we can overfit to. So in most of the architectures where the 20% of improvements are reported, if you compare it to, if you will evaluate it on the prospective data, so real undersampled reconstruction on the scanner, where we have a bit different magnetic gradients, and therefore we have a little bit more of artifacts that are not incorporated in the model. In these cases, the model, a lot of machine learning models can start to degrade. So from my perspective, the further steps where the variational networks can be improved is to learn the operator correction. So here we assumed some variational linear system as an operator. We can try to correct it using some more sophisticated simulators. And also, for me, I think that it's worth not looking for better priors for images or better optimization methods, but because there is nothing more to gain, I think that the design of the acquisition sequences and the acquisition protocol is how we can improve the quality of the acquired images. Okay, so thank you very much for your attention. I think I was a bit over the time, but.
Thank you very much, Valery. It's a very nice talk. I guess we can move to the discussion part. Are there any questions for Valery?
Can I ask one?
Yes, of course.
Hi, Valery. Thank you very much. It was actually a very nice summary, and you put
Hi, Karen.
on. Hey, you put everything on top of each other very nicely. Thank you very much. The question is following up on what you said before. Do you think so then now that we have these very crazy good reconstruction algorithms and so on, which require very little fine tuning by hand and so on, do you think one should go back to acquisition and then adapt really acquisition to sort of to see the benefits of these reconstruction algorithms better? Because until now we have been sort of optimizing for like hand tunability and like seeing the image by ourselves as humans, but maybe rather we can like incorporate acquisition to further these reconstructions.
Yeah, I think so. Well, that's at this point, that's my primary area of interest. For example, optimizing undersampling patterns, of course, but also I think MRI is a very good example because unlike CT machine, MRI is a very sophisticated physical instrument where you can do so many different experiments. Most of them will give you unreasonable results, but you have to find one that extracts the information you need. And yeah, so I think that there can be a lot of progress be made in this area. Another also area, I think that, well, for some application, we might not need intermediate representation as a reconstructed image. Probably people like I personally would love to see the image. If any, I don't see it being incorporated into clinical practice, but maybe we just don't need to do reconstruction. Maybe we need some better intermediate representation for the image that is not too big, but can be used in image analysis problems like, well, of course, segmentation and anything else.
But so you think that it is practical actually that we sort of use deep learning, whatever, to affect back how we acquire images by also looking at the physics of the acquisition and so on. So that could be like a practical way of.
Yeah, so also a little bit like follow up to what I said, that people are not very good in image reconstruction, right? And it's kind of, it's unusual for machine learning. And however, for now, people design the imaging experiments. So we know that people are good at it. And I think that's exactly where we should put artificial intelligence. So I don't want my variational networks to be too intelligent. I don't want the variational network to understand that it expects to reconstruct a heart, because what happens if, I don't know, there is no heart, or, well, that's or a stretch example, but you see the point.
Yeah.
You don't want to hallucinate. And for now, I think from my perspective, the variational network or the loop unrolling approach is, so theoretically doesn't give you this guarantees as most things in the machine learning, but from my experience, it's it generalized unbelievably well.
Thank you very much.
Thank you for a nice talk. I have questions. What limit do you, or what do you think the limit of these variational networks are, or how much can we undersample the image basically now? Now I saw it was ×4 and ×8, but.
So sorry, the limits in what term the limits of the variational networks? You mean
so the limits in undersample factor?
Well, I think that, yeah, I cannot give you an exact number because you can make your imaging even more adaptive. For example, if you have 25 cardiac phases, maybe at some point you, in some scenarios, the heart motion can be very regular, and you can average a lot in time for some segments of some parts of the cardiac cycle. For some, heartbeat can be very irregular. But okay, so reasonably, for 4D flow MRI, and we have a lot of data, right? So 4D data tensor, so here we report result for acceleration factors of up to 22. And some other people also report this to a factor of 22, but the prospective study that we had was at acceleration factor of 12. So I think that 12 or 15 is, for now, for multidimensional data, is the reasonable expected acceleration rate. But of course, you can think like, if, for example, you have not flow data, but just a beating heart, you can think about that you don't want an image of the heart, but just a segmentation of the heart. And then there were works that show that you can go to an acceleration rate around 100. So something very awful, but quite cool.
Yeah, thanks.
I also have a question. So this very nice story that you presented, where you start from like the classical methods, where it's basically very low number of learnable parameters, just the step of the gradient descent, and then the regularization, the weight for that. And then you gradually started increasing degrees of freedom of the model, right? So, so making the derivative operator learnable, and then the activation function learnable. So, and if we just keep going on that path, the other end of the spectrum would be to have a completely black box model, right?
Exactly.
So, how can one decide where to stop on the spectrum? So is it just based on empirical results, or there can be better?
Yeah, I think it's always like this. It's empirical. Well, I mean, I think that so here we added something like five different tricks, 5 improvements to variational networks, and I mean, generally speaking, for unrolled gradient descent iterations, I cannot think of anything more. You can think you probably will be better just adding up layers, and I think the improvements that you might want to incorporate in the reconstruction problem should be a bit different at this point. So, for example, when you reconstruct MRI images, you also know, so you have different scanners, 3 Tesla, 5 Tesla, you have different, you can have some acquisition parameters be a little bit different. So T1 and T2 times, right? There can be a slight difference, and those can be used as an input to, so where was it? 1 second. Those can be used as an input of this modulator functions, for example, psi-d, right? So here they depend only on the acceleration rate, and those are scalar functions. But you can make those functions to depend on, well, not only the acceleration rate, but the pattern of the mask. That's what we did recently. Because if you have a lot of samples in the center of the K-space, you have very different, like you have basically the knowledge about the low frequencies, but don't have a knowledge about high frequencies. So the reconstruction will be very different. So you can put the full mask, you can also put T1 and T2 times for this acquisition. And now this will be a neural network that maps something like Rn into R. And it just modulates one of these data terms. Also, yet another idea is to, it depends on what you need, right? So if you want to, you can make the network stochastic. So basically you can make a separate network that generates randomly, basically the parameters of the variational networks, of the variational network. And also there might be some interest in if you can employ if you know something about the structure of your acquisition matrix, you can choose a different algorithm, not gradient descent, but you can enroll ADMM. And when you enroll ADMM, you can make so many choices like how you split the operators. So there are a lot of optimization methods, what I mean, and different optimization methods are suited for different problems. Some for sparse matrices, in some cases we can factorize parts of the problem, etc. And incorporating more knowledge about the model and about the matrices and kind of marrying them together with this variational networks, I think you just have to follow the formulas how they evolve. But I drew my inspiration from the classical reconstruction methods.
So, but would you say that the advantage comes that the advantage of these model-based approaches comes that you already know the model and you know it up to some parameters. So you only want to learn these parameters. So is the advantage coming from reducing the number of learnable parameters and thereby avoiding overfitting? Is this the main kind of theme of the idea?
Yeah, I think so.
Okay.
I think that just this problem doesn't need a lot of intelligence, artificial intelligence.
Yeah.
And we can clearly solve this problem good enough, like not perfectly, but good enough without any machine learning. Then why not to take this solution that we already have? You can initialize your filters and all your scalars based on the regularization you choose. You can choose your initial point and then you can fine tune it. And also from experience, you can reduce the modal complexity. You can make the network as simple as we started with, only learning the some of the very simple activation functions and the step length. And then this model will be extremely fast for the evaluation. So for example, if you consider the problem of acquisition design, you have one model that, so we have it here, right? So in the acquisition design, you basically will have a model, some forward model f of x, parameterized by some parameters, omega. And you would want to generate the data according to this model, tuning omega, and then reconstructing it back with a variational network, right? That has parameters theta. And then you have to calculate a lot of gradients of a lot of terms with respect to each other. And then big models will just not work on the current, well, at least on our GPUs. So very often when you need, sorry, I'm wandering around it, but there are a lot of benefits. And just to give you one example, sometimes you might want to have, you want to model the full pipeline for estimation of some tissue parameter, and the image reconstruction can be only part of it, or it might be, it might not even be needed to reconstruct what we want, but it can be used as an additional information. So we can provide very simple networks that are quite fast and have very little parameters, but they can be tunable and they can provide this this estimates quite accurately.
Yeah, thank you. Are there more questions for Valery?
Maybe a little following up on this. So if I understand correctly, there's no need for this operator to be linear, right? This forward model.
Yeah, exactly.
And so your point, you're arguing you don't want to make this operator, you don't want to introduce parameters here, because then it's, I don't know, then you get too much artificial intelligence. Did I understand it correctly?
Do I have those? If you look at this iteration, that classical variational network iteration, right? So this is maybe let's use better this one. exactly. So we started with this optimization problem. We took the gradients, right? It's the gradient of the data term. It's the gradient of the regularization term. And this parameter that weights them it's done to optimize better. So, and we don't modify initially this data term because, well, we use, in undersampled reconstruction, we just undersample the data, right? We calculate the Fourier transform on a computer and undersample it. So we assume that the model is followed exactly, plus some noise on top. But there can be some systematic errors in a scanner due to a lot of different artifacts. And however, we cannot learn them because we don't have paired training data from the scanner usually. It's very hard to design such experiment. And therefore, we cannot learn too much more about the image synthesis model here. That's why initially it wasn't touched, it wasn't modified. No degrees of freedom were added. However, then we add some degrees of freedom but based on a different intuition. So we learn preconditioner, and it doesn't affect yeah. So it's again only hand wavy arguments can be applied here, I'm afraid. But you can also imagine that you can make this the neural network to follow the acquisition model AX strictly. For example, in case of undersampled MRI acquisition, you have underdetermined system of linear equations. And then after the neural network, you can actually project this estimate, the reconstruction. You can project it to an image that fulfills the, let's call it F undersampled X equals S, right? Undersampled. And this is underdetermined system. It has infinitely many solutions. But among all those solutions, we might choose the one that is closest to the neural network estimate, right? But if you project on these equality constraints, you will guarantee that, well, at least you fully explain the samples that you actually acquired. Yeah. So, like if the question was that, why didn't we introduce any degrees of freedom to the data term initially?
Yes. Yeah.
So that was the reason, and there are a few ways to, and if you think about it, it's exactly what we incorporated in the variational network. We know the image synthesis process, so therefore we can at least avoid relearning it because we don't have anything better at this point. And but generally, if you have training data and you want, and you can simulate stuff with the forward model, and then you want to project back, you can approach it simply like a regression problem, right? And then take arbitrary neural network architecture, take fully connected neural network, and then you will relearn the Fourier transform, and you will also learn to provide an estimate and the image prior. However, this model was the fully connected network is exactly the AutoMap architecture, and you see the amount of weights it has, an amount of training, and it's not scalable, and it's, I don't see it being used anywhere, like except manifesting the results.
Thank you.
Can I ask a technical question?
Yeah, of course.
Can you explain the modulation again that you use for the generalization for different undersampling factors?
Oh yeah. It's so I think that you're now also referring to the paper, because I actually forgot to mention the generalization with respect to undersampling rate. Yeah. So first, I didn't mention it, but here you can see that in this MRI problem we had very limited data. But if if I provide you one network that can reconstruct at least training data, well, it will be much more convincing if I would say that it works for a range of the acceleration rates, because, well, you can see here this aliasing artifacts. They look quite different for different acceleration rates, and it adds variability to the training data, effectively. So the network sees more and more diverse data, and the diversity comes from the fact that we allow different acceleration rates. And I think that it can be seen as some sort of implicit regularization. So if it addresses the question, I'm not sure.
If there are no final questions, maybe we can thank Valery for the excellent talk. And it was very engaging, clearly by the amount of questions, also very relevant for us in what we do in the group. So thank you very much. And yeah, bye.
Yeah, thank you.
Thank you very much. Thanks a lot.
Bye. See you around.